Okay, good afternoon, all of you. I hope I am audible and
Yes, sir.
PPT is
Audible.
also visible.
Yes, visible.
I think we shall wait for maybe 1 minute or so for participants to join back and then we will start. Okay, we shall begin now. Good afternoon, all of you. I welcome you back to the fifth session of Faculty Development Program on Computational Fluid Dynamics for Beginners, uh, sponsored by AICT under Atal Academy. So far, we have looked at the overview of the computational fluid dynamics. Then we also looked at all the governing equations in computational fluid dynamics, uh, the nature of the boundary conditions, the initial conditions, and so on and so forth. And in today's lecture, we also looked at the finite volume methodology for steady state uh, heat conduction problem. Today, in this particular session, what we will do is that we will look at how to apply the finite volume methodology to unsteady state conduction problem with heat generation. One second. Sorry for the discontinuity. Uh, so in this particular session, we will look at the conduction equation with heat generation, and we will try to understand how to apply the finite volume methodology to such a problem. In order to understand this problem, we will again consider the same square plate as we considered in this when we dealt with the steady state problem. We will consider the same domain. We will also try to understand how to do the grid generation, and then we will look at the actual uh, finite volume methodology for discretization of the equation. We will go term by term. In the last session, we dealt with steady state wherein there was only one term, but here we have more than one term, and hence we need to look at the discretization term by term, and then we will combine all those terms together. We will formulate the algebraic equation, and then we will try to understand how to solve the algebraic equation uh, using certain methodologies. There are implicit and explicit methodologies which are available. We will try to understand those methodologies. So the feed generation is again the same. I am reiterating it again so that the fundamentals about the grid generations are fortified, strengthened. What we do, we draw some horizontal lines, vertical lines, and divide the entire domain into small control volumes, which are represented in terms of cell centers. We also assume that there are some cell centers on the boundary itself, and these boundary cell centers are represented by yellow circles here. And we assume that these cells, which are formed around blue cell centers, have the zero volume as such. So this is just an assumption. So these are the cell centers around which there are cells but with a zero cell volume. The yellow cell centers with a dark, thick border, black border, are the border control, so border cell centers, and these are the interior cell centers. P is a representative cell center, and E is the east neighboring cell center. W is the west neighboring cell center. This is north and this is south. These are again nomenclated as I discussed in the morning by running indices I and J. For boundary control volumes, that is for blue control volumes, we have the running indices as I is equal to 1 and I is equal to 1 and I is equal to I max, and J is equal to 2 to I max minus 1. Similarly, for horizontal boundaries, we have J is equal to 1 and J is equal to J max, and I is equal to 2 to I max minus 2. Sorry, I max minus 1. Sorry. So these are the running indices for blue cell center. For interior control volumes, pure interior, excluding border, that is from here onward to this, I is equal to 3 to I max minus 2 and J is equal to 3 to J max minus 2. These are interior. Border control volumes are I is equal to 2 to I max minus 1 and J is equal to 2, or J is equal to J max minus 1 also. These border control volumes are I is equal to 2 and I is equal to I max minus 1 and J is equal to 2 to J max minus 1 and J is equal to 2 to J max minus 1. So this is a discrete representation of the domain, heat transfer domain, which is nomenclated using running indices I and J. Then we calculate we do the grid generation. I mean to say, we try to obtain the geometrical parameters. What geometrical parameters are obtained? We need to obtain the x coordinate and y coordinates of each cell center, all the cell centers. And that is found by considering the x and y coordinates of the vertices. The vertices, the x coordinates of all the 4 vertices of each cell are summed up and divided by 4. So xne, x plus xse plus xxw, xnw divided by 4, that gives you xp. Similarly, you can determine yp. Delta x and delta y, these are the sizes of the faces. We have east, west, north, south faces. Then we also need to determine the distances between the cell center under consideration and neighboring cell centers. For example, delta xw, this delta xw is this delta xw is the distance between cell center under consideration and neighboring cell center. That is given by xp minus xw. Delta xp is given by xp minus xp. Similarly, delta ys is given by yp minus ys. Yn is given by yn minus yp, and so on. We also calculate the areas of the faces. Area of east face is delta AC, which is also equal to delta y. Delta AC equal to delta y. This typographical mistake is carried forward here. Please consider this as delta y. So this is delta AC is equal to delta y. Delta SW is equal to minus delta y. As I said, area is a vector quantity. So if the heat is going through this, it is positive, and if we consider this as positive, this area is negative. Similarly, delta Sn is equal to delta x, and delta Ss is equal to delta minus delta x. So again, this has to be swiped. We need to calculate the volume also. In the earlier steady state problem, we did not require the volume, but here we will be requiring the volume also. So this is the volume of the cell is given as delta Vp is equal to delta x into delta y. So this is the grid generation we carry out. So how do we calculate the geometric parameters? For example, delta x we can calculate by using simple expression L1 upon Imax minus 2. Delta y is equal to L2 upon Jmax minus 2. Now I have included this because last time somebody asked me how to do the coding. In the coding you can include these kinds of equations. Delta S is equal to delta y, delta SW equal to minus delta y, delta Sn equal to delta x, and delta Ss equal to minus delta x, and delta Vp, delta Vij you can say is delta x into delta y. So these are some of the geometric parameters which you need to calculate as a part of grid generation. The geometric parameters are required to be calculated for all the control volumes, like delta xw and delta xe is delta x, and delta ys is equal to delta yn is equal to delta y, except for left border control volumes, right border control volume, bottom border control volume, or top border control volumes, we have a separate expression. Delta xw is equal to delta x by 2, delta xe is equal to delta x by 2, delta ys is equal to delta y by 2, and delta y is equal to delta y by 2. We have seen these kinds of geometric expressions in the last session as well. The governing equation is like this now. If you look at the energy equation, we have Cp del by del T of rho T, and then we have a convection term. But since in this, while understanding the solution of unsteady state heat conduction problem. Only because we are considering only heat conduction problem, we are not considering the convection term. So we have done away with the convection term in the energy equation. And now we are left with unsteady term on left hand side of the equation, and this is conduction term or the diffusion term on to right hand side of the equation plus heat generation. So this is my governing equation in the differential form. What we will do, we will take up each and every term in this equation and we'll try to apply it to a small control volume. We will discretize it, and once we discretize it, we will discretize all the terms. We will put all those terms together to formulate the entire equation. And once we have the entire equation, we will try to look at the solution methodology to obtain the solution for temperature. To remember, our objective in the unsteady state heat conduction problem is to obtain the solution for all the xy locations at all the time instances. So T is a function of x, y, and time. Capital T, that is temperature, is a function of x, y, and time. So that is the objective. Once you get the temperature distribution, you can find out the other parameters like heat transfer across the phases. So let us look at the first term. The first term is the unsteady term. When we apply the first term to a small control volume, when applied to a small control volume, it's representation in the integral form is Cp integral over delta Vp of del by del T rho T dV. That's an exact representation of unsteady term as applied to a small control volume represented by P. So this small control volume consists of many particles. I can say infinite number of particles. And each particle may have a different value of del by del T rho T. This differential may have different value of for each and every particle. Sorry, somebody had joined, so I had to. So what we do, we assume that there is a certain mean value of that del by del T of rho T. And that mean remains constant for a particular time instant. And thus we take it out of the integral sign. What is left inside the integral sign is dV. And then integral of dV is delta Vp. So my equation changes to Cp into del by del T of rho T mean into delta Vp. We further assume that, and we introduce the approximation here. We assume that this mean is also equal to the value of the derivative at point P. So this equation now changes to Cp into del by del T of rho T at point P into delta Vp. Del by del T of rho T at point P into delta Vp. So this differential at point P can be replaced in terms of temperature at two consecutive instances of point P. Temperature, this different derivative can be replaced by considering temperature at two consecutive time instances of point P. So rho is assumed to be constant, is taken out of the derivative sign. Then rho delta Vp Cp, this delta Vp is taken out to this side. Rho delta Vp Cp into Tp at n plus 1 level minus Tp at nth level divided by delta T. small delta small t. What is Tp at n plus 1 level? N represent a time instant. So if n represent first time instant, this is my second time instant. Or if n represents the current time instant, n plus 1 is the next time instant. Or if n plus 1 represent the current time instant, n represent previous time instant. So essentially, we take into consideration the temperature at two consecutive time instances, which are delta T, which are separated by duration of delta T. We take into consideration the temperature difference between two consecutive time instances, which are separated by time duration of delta T. So Tp at n plus 1 minus Tp at nth level divided by delta T represents del T by del T. Rho is taken out of the derivative. So rho delta Vp Cp Tp at n plus 1 minus Tp at nth level divided by that is the discrete representation of an unsteady curve. I hope this makes sense. I hope I'm audible properly. I hope I'm audible. Somebody is saying half of the PPT is not visible. Is that true with all of you? Anybody can respond, please. Is it that my PPT is not completely visible to you?
Sir, like it's not full screen, so they might be saying like that.
See now.
Visible clearly,
Now,
sir.
no,
Visible.
but one participant has complained that in this mode it is half visible. Is it true?
No, sir, full visible, clearly visible.
So maybe the problem may be at his end. Okay, no problem. I request the concerned participant to please check your own settings. So this is the discrete representation of unsteady term in the governing equation. Again, let us go to the second term. Second term in the equation is k grad square t. This is grad square t. If it is a Cartesian coordinate system, is del 2t by del x square plus del 2t by del y square. Now this has to be discretized, k grad square t. So we'll pick up this term. We'll make its exact representation for small control volume represented by P. So integral over V delta V k grad square T dV is the integral representation in the integral form. K is assumed to be constant. It is taken out of the integral sign, and then volumetric integral is converted into surface integral. When we convert it into surface integral using Gauss divergence theorem, one of the grad goes away. So and the volumetric operator changes to surface operator. So integral over delta S of delta T dot n cap ds, as we have done in the morning also, is the representation of the diffusion term considering the surfaces. So this integral is on the entire surface, all the four surfaces together. We can disintegrate it. I mean, we can divide it into four different surfaces: east, west, north, south. So I can write down first integral as integral over delta S east grad T for east face into DSE. For west face also I can write them similarly. K into integral over delta SW grad T for west face into DSW for north and south faces similarly. And then we can sum it up for all the faces. So I get equation K into summation over the faces east, west, north, south of integral delta SF delta T by delta N at the corresponding face into DSF. Now we further assume that this derivative is constant, which can be obtained in terms of the temperature at P and temperature at E. By taking temperature difference between the two and the distance between two, I can find out the temperature gradient here, and I assume that the same temperature gradient prevails over the entire face, and then I take it out of the integral sign by assuming it as constant. What is left inside the integral sign is DSF. So approximate representation now goes like this: summation over east, west, north, south faces of K del by del N over the face into integral over delta SF DSF. And integral of DSF is delta SF. Now look at this quantity. This is the product of thermal conductivity into temperature gradient. What is this? It is a heat flux because of conduction. This is heat flux because of conduction. Or I can say diffusion heat flux. So I represent it as FDFT. Integral of DSF is delta SF. This is nothing but diffusion flux across the surface, and diffusion is of heat, and hence I am designating it by T. FDFT is diffusion of heat across the surface, across the face. That face may be east, west, north, south. Do remember here, your delta S is delta Y, your delta SW is minus delta Y, delta SN is delta X, and delta SS is the minus delta X. And diffusion flux into area gives you the total heat transfer. So FDFT into delta SF represent total heat transfer across one face, and if I sum it up for east, west, north, south, I get a total diffusion total heat transfer because of diffusion across all the faces. What I get is total heat transfer because of conduction across all the faces. That's what is represented by this term. And in that, this flux value can be calculated by considering K into del T by del N. That is my flux. So diffusion flux is FDFT, heat transfer rate by conduction. Then the discretized form of diffusion term for control volume T can be written as, which represent essentially the net conduction heat transfer rate into the control volume. And this conduction into the control volume occurs through the faces. Remember that. And hence, it has to be summed up over east, west, north, and south faces. DPT, that is the total diffusion occurring across all the faces of a control volume, is summation over the faces east, north, west, and south, FDFT delta SF. So this is my DPT. And how do I write it? FDFT for each face I can write as TE minus TP divided by delta XE into K. See, for east face it is TE minus TP divided by distance between two delta XE multiplied by K. That's a flux. And to that, if I multiply by the corresponding area, I get total diffusion across east phase. Similarly, Tp minus Tw upon delta Sw into delta Sw. Tp minus Tw divided by delta Sw, this distance. Multiplied by K is a flux, and to that if I multiply it by the area delta Sw, I get the total diffusion across west phase. Similarly, this is across north phase and this is across south phase. I hope you understand. Similarly, we can discretize the source term. The exact representation of the source term using integral form is, when we apply it to a small control volume, is integral over delta Vp of Q bar dV. We assume that this Q bar is a heat generation rate per unit volume. So there are n number of points, there is infinite number of points within this control volume. But all those points may have a certain mean value of a heat generation rate. We assume that that mean value is constant and we take it out of the integral sign. What is left inside the integral sign is dV, and integral of dV over delta Vp is delta Vp. So the further representation is Q bar mean into delta Vp. We further assume that this mean value is also equal to value at P. Thus, I approximate it as Q bar P into Q bar P. This Q bar mean is approximated as Q bar P, and Q bar P into delta Vp is your, I am designating it as SPT. I am designating it as SPT. That is a source of heat which represents the heat generation. So all these terms are now put together in the diagrammatic form here. So I am trying to give you here the physical understanding of the unsteady state algebraic equation. So I can write down this equation directly also. See, my Tp is changing from Tp at nth level to Tp at n plus 1 level. That's one thing. And then there is a conduction heat transfer, which is, if I consider the west phase, minus k dt by dx at W into delta y is the conduction heat transfer across west phase. Here, I am assuming that all the incoming heats are positive. So here heat is coming in the negative x direction, so minus k becomes plus, so k dt by dx at east phase into delta y. Here also minus k dt by dx, dt by dy, here it has to be dt by dy into delta x. That's my total heat transfer because of conduction across the south wall, south phase. And here it is north phase. So if I add all these four, what I obtained is dPt, that is kept here. So my unsteady term is rho Cp Tp at n plus 1 minus n Tp at nth level upon delta T into delta Vp. That was the discretized form of my unsteady term. It is here. And then there is dPt, which is the summation of all these four heat transfers across four phases, plus SPT. That is, this is the governing equation in differential form, and this is the governing equation in the discretized form, or it is a finite volume equation, which is also called finite volume equation. Or as yesterday Professor Atul Sharma said, it is a linear algebraic equation. So it is this equation which we need to solve to obtain the values of Tp at n plus 1. We want to find out if we know the temperature at a particular instant, then we need to find out the temperatures at all the cell centers at next time instant. That is the objective. That is, we want to find out temperature as a function of x, y, and time. that is T. I hope this makes sense. So now, having written this equation, do remember this dpt is in the discretized form. I have already given you the expression for dpt. It is in the discretized form, and q bar p delta vp is also a discretized form, which is spt. So the entire equation is the algebraic equation in the discretized form. Now I can apply this equation to each and every cell, and we can scroll through the cells one by one and obtain the values for next time instant. There are two different methodologies available to obtain the solution. The first method is called explicit method. In explicit method, what we do, we write down this dpt at nth level, that is at previous level. We also write down spt at nth level, and we write down the unsteady term as it is. It is tp at n plus 1 minus tp at nth level divided by delta t into delta vp. So now, if I write down it like this, if I know the initial conditions, I can calculate dpt at nth level. If I know the initial conditions, I can calculate this dpt. The plate is, let us say, kept in the furnace. It is taken out of the furnace with a certain temperature all over the plate. Let's say it is somewhere around 50 degrees Celsius. So my temperature, the initial condition in terms of temperature is Tij for all interior control volumes, cell centers is 50. The boundary conditions, anyway, we need to implement as we have discussed in the earlier session. So dpt is written at initial condition. SPT is also written at initial condition. So this is completely known to me. This is completely known to me from my initial conditions and maybe boundary conditions also. What is left to be determined is TPN plus 1, because TP at nth level is also known to me from my initial condition. Delta T is the time duration which we need to decide. How to decide? There is a stability criteria. We'll talk about that. And these are the properties which are known to us. So if I write down dpt at n plus 1 n level and spt also at n level, and apply this equation to one cell center, let's say I apply it to this cell, I can calculate dpt by using information here, 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 here from the previous instant. That is from the initial condition to begin with. SPT also I can calculate. Then TP at nth level is known to me from my initial condition. For example, this point. Then TP at n plus 1 level is to be determined. And I can do that because I know the information at nth level everywhere. I can go to this point, switch over from one point to another point, and can find out the information of TP at n plus 1 level for all the points. So in this methodology, explicit methodology, I write one equation, I have one unknown. I write second equation for second cell center, I have one unknown. I have third equation for third cell center and one unknown. Keep on writing equations and keep on solving those for each. So that becomes an explicit method. For this explicit methodology to work properly, there is a stability criteria. And the stability criteria is alpha into delta t into 1 by delta x square plus 1 by delta y square should be less than half or equal to half. It means if this is not followed, my solution will not converge. What does it mean? What are the implications of this? Here alpha is a thermal diffusivity, which is rho Cp by K. Sorry, rho, which is K by rho Cp, thermal diffusivity. What is the implication of this equation? See, if I want the solution at large number of points, my delta x and delta y will be small. If this becomes small, delta x and delta y become small, the bracket value may increase. In order to reduce that, I need to multiply by smaller value of delta t. Because alpha is my property of a solid which cannot be changed. So what I can do, I can change delta t. So if you are using this explicit method, and if you want solution at large number of points, your delta x and delta y will be smaller. And in that case, you will have to use a small delta t value. Otherwise, your solution may diverge. You may not obtain the converse solution. So this is called the explicit method. Here I have shown you some equation which can be formulated. This is just what we can do, we can collect all the terms having multiplier as Tpn plus 1 together. Put those terms in one bracket and take Tpn plus 1 out of the bracket, and then the bracket will represent AP. Similarly, we can do it for T east face, T north, T south, T west, and then in all the terms with T capital E can be collected together. T capital E is a multiplier. All the terms can be collected together and put into one bracket, and then TE can be taken common, and then what is inside the bracket will be T capital E, A capital E. Similarly, I can find out A capital W, A capital N, and A capital S, and so on. And whatever are the terms which are left, we can put those terms in the B. So that helps us to obtain this solution for Tp at n plus 1 level. This is the easy way of representing the equation. But essentially, our Tp at n plus 1 is the unknown when we are using the explicit method. However, when we obtain the solution using explicit method, there is a stability requirement, and that is alpha delta t into 1 by delta x square plus 1 by delta y square. That should be less than equal to. There is another method called implicit method. In implicit method, what we do, we write down the diffusion at n plus 1 level. And we don't know the temperatures at n plus 1 level, but we write down the equation. We also write down SPT at n plus 1 level. So when and then unsteady term is written in the same fashion as we did it for explicit method. So in this, if I write down this equation, such kind of equation, to let's say the first point, first cell center. This is unknown to me because I have to write it at n plus 1 level. This is unknown to me. This is known because it is known from the boundary condition. When I come to this point, this is unknown, this is unknown, this is unknown, but this is known. Similarly, when I come to this point in the same fashion, this is unknown, this is unknown, this is unknown, this is unknown. Even Tp at n plus 1 level is also unknown. Only known is Tp at nth level. So when we make use of implicit method like this, if I write down this equation for all the interior cell centers, I will have as many unknowns in the equations as the number of cell centers are. I hope you are following me. See, when I write the equation for this point, this is unknown, this is unknown. When I write equation for this point, this is unknown, and that point itself is. Thus, if I scroll through all the points and write down, let's say 25 equation for 25 cells, how many unknowns I will have? I can write down 25 equations for 25 cell centers. How many unknowns I will have? Anybody can respond. How many unknowns I will have? I will have 25 number of unknowns. It's not possible to go beyond 25 because I want to calculate the temperature at 25 points. I will have 25 unknowns only. Am I audible or not? Nobody is responding, so I'm.
Yes, yes.
Okay. So I will have 25 unknowns, and I can write down 25 equations. So 25 unknowns and 25 equations. I can solve those equations simultaneously. So I can solve these equations simultaneously. This method of obtaining the solution to solve the equation is called implicit method, and it does not require any stability criteria. That's the beauty of implicit method. Implicit method does not require any stability criteria. However, explicit method requires stability criteria. Here, I am showing you both the methods diagrammatically. In explicit method, let's say this is my nth tensile of the grid. And from nth time instant, I want to switch over to n plus 1. Now, this tensile is known to me from the initial conditions and the boundary condition. Temperature at all these yellow circles is known to me from initial condition. When I take the plate out of furnace, I know its temperature. And after delta T time, I want to understand what will be the temperatures at yellow cell centers. So I want to find out the temperatures at all these yellow points. So I scroll through. When I want to find out the temperature at this yellow cell center, I need the information from previous in the explicit method. Previous cell centers at previous tensile. If I want to find out the temperature here, I need to know the information here and all these 4 neighbors. Then I can find out the temperature here. In implicit method, what we do? If I want to find out the temperature at this point, I write down equation in terms of the neighboring cell centers at the same level, that is n plus 1 level itself. And I use the information of a cell center under consideration from previous cell. And that's the only information we use from the previous cell, previous time instant. But here I can write down, for example, in this case, 9 points. So I can write down 9 equations and solve those 9 equations simultaneously to obtain the solution at all these 9 points. This is called implicit method. I hope I am able to make the sense. Explicit and implicit methods has got certain advantages, disadvantages, which are enumerated here, which are written here on the slide itself. It's very straightforward to understand. In an explicit method, it's relatively simple to set up the program. The reason is that we have one equation and one unknown kind of situation. So we can solve that situation very easily, and hence explicit approach is relatively simple to set up the program, set up and program. But the disadvantage of explicit method is that it results in long computer times to make the calculations over a given interval of time. Let's say, for example, I need to do the simulation for 10 seconds. The value of a delta t I need to use has to be as low as possible so as to have the stability of solution. So if you keep delta t smaller, let's say if I keep delta t 0.1 for carrying out the simulation up to 10 seconds, I will have to do the 100 number of iterations if delta t is 0.1. And in order to obtain this stable solution or converse solution, I need to keep delta t as small as possible. So on the contrary, in case of implicit method, my delta t doesn't matter. My implicit methodology gives me stable solution, and there is no stability criteria in terms of delta t. So if I want to do the simulation for 10 seconds, I can use, let's say, 1 second as a time duration, and then I will have to do 10 iterations only. And within 10 iterations, I will obtain this required solution. However, in case of explicit method, we need to keep delta t value as small as possible. So if I, for example, if I keep it 0.1, I will have to do 100 iterations to obtain the solution after 10 seconds. So, and the implicit method has got advantages, considerable fewer time steps to make the calculation over a given interval of time. So although this is the advantage, but the computer time per time step is much larger in case of implicit method because we need to solve the equation simultaneously. So that's implicit and explicit approach. Now here I'm giving you the solution algorithm for explicit method to obtain the solution for unsteady state heat conduction problem. The first point is enter the inputs. Input consists of material properties like we need to give K, that is thermal conductivity, and geometric parameters like L1 and L2, maximum number of control volumes in X and Y directions, boundary conditions input, if any. For example, we need to give the value of H, that is heat transfer coefficient, if we are using a Robin boundary condition. And EPS. EPS is epsilon, which we use for deciding the convergence criteria. Then the next important step is a grid generation. We calculate all the geometric parameters of all the control volumes as a part of grid generation. We have seen this in the morning also, so won't be using too much of. I will not be spending too much of time now. We will calculate delta t using stability criteria. Stability criteria is given to you here. We can use this stability criteria. We can equate this with that of half, and we can calculate delta t. And set the initial value. Do remember, while dealing with the problem, I said it is initial guess, but now this is initial value, the actual temperature at the beginning. It is also called initial condition. Set the initial condition for Tij at n t, that is set Tij at nth level, and the Dirichlet boundary conditions for temperature. If there are Dirichlet boundary conditions, those also can be set. Then you can set the other non-Dirichlet boundary condition. I have given you the explanation why non-Dirichlet boundary conditions are required to be separately incorporated, because non-Dirichlet boundary conditions are subjected to updation as we proceed through iterations. Having done this, you can set all, we can assign all Tij values which we have so far to T old Ij. We define certain other variable T old Ij, and we assign all the Tij values to T old Ij. That is T Ij at nth level is equal to Tij at n plus 1 level for all control volumes. Then for each interior control volume, we calculate the total diffusion Dij nth. So D, that is total diffusion across all the faces of a control volume using old data. And then we calculate Tij at n level. This is at n plus 1 level. This is new value. We scroll through all the points and find out the new values of temperatures, and then we check for steady state by considering RMS value. It is summation over Ij of Tij at n plus 1 minus Tij at nth level whole square divided by Imax minus 2 into Jmax minus 2. Imax minus 2 into Jmax minus 2, which I am considering here, is the total number of yellow cell circles at which the solution is sought. If this value is less than epsilon, my solution is obtained, else we need to go to step number 5 and repeat the entire procedure. I hope you are able to understand the solution algorithm. Now, this solution algorithm can be converted into code. You need to get acquaintance with any of the languages. Many of the participants have asked this question: which language we should use? I mean, it's your choice. In fact, even you can use MATLAB, you can use C language, C compiler, or Fortran compiler, or whatever. And nowadays, even the Python is also there. You can use any of the languages, but the basic algorithm remains same. The solution can be plotted. Here I am sharing with you the solution which has been obtained for 1D steady state conduction, 1D unsteady state conduction. When it is 1D, the temperature here is TB1 and temperature here is TB2. When it is 1D, we need two boundary conditions. Let's say TB1 is 0 and TB2 is 100 degrees Celsius. So heat will be transferred from this end to this end. And then I can assume Ti, that is temperature, initial temperature, as 30 degrees Celsius. And then if I apply this solution algorithm, I can capture the solution at any time instant as per my requirement. So I am here plotting this. Do remember, this problem is intrinsically steady. So in due course of time, you may obtain a steady state solution and you may have a linear variation of temperature like this, a straight line. But the solution which I'm sharing here is the solution captured at a certain time instant before steady state has reached. And then I can understand how the temperature varies. It varies something like this, which may become a steady state solution when my variation is linear like this. Here is the solution for 1D unsteady state heat conduction with a different boundary condition plotted. The TB1 is 100 here and H and T infinity is given. H is 100 watt per meter square Kelvin and T is infinity is 30 degrees Celsius. So this is not the solution which is steady state solution. The solution is captured in between. I'm going to share with you a small animation and I'll be talking about the solution of 2D two-dimensional unsteady state heat conduction. So I have just plotted a temperature variation at one time instant, but I can plot temperature variations at several time instances. And if I superimpose those, I can even create a movie to understand how the temperature varies with respect to time. If all those variations are brought in front of your eyes one by one, then it will be helpful to understand the variation with respect to time also. Here I am trying to show you, I have shown you a variation with respect to x at a particular time instant. Similarly, here is a 1D unsteady state heat conduction with heat generation. The boundary conditions are TB1 is 0, TB2 is 100 degrees Celsius, and when there is heat generation, there is a heat generation of 30 kilowatt per cubic meter. Then at a particular time instant, how the temperature looks like, and then when the steady state is reached, how the temperature looks like. That is when the steady state is reached, because there is a heat generation, the maximum temperature is reached somewhere in between. It's not at the end. Because of heat generation, there is a rise in temperature in the run. Similar kinds of solutions are available. Here I am sharing with you and the implementation solution obtained after implementing the same algorithm, but it has been implemented for 2D. Here again, the boundary conditions are 100 degrees Celsius, 200 degrees Celsius, 300 degrees Celsius, and 400 degrees Celsius. But the solution which now appears in front of you on the screen is not the steady state solution. I am sharing with you here the unsteady state temperature line and flooded contours. You remember in the morning I showed you only line contours or only flooded contours, but it is also possible to combine both together, and we can also look at the solution in terms of line and flooded contours. The color of each band actually indicates certain temperature. Similarly, the lines can also be labeled with the temperature. These numbers which I am showing here are nothing but the numbers. These numbers represent the temperature at that location, the location through which the line passes. So these numbers are called labels. The contours are essentially labeled. These contours are drawn by using a software called TechPlot, as I said in the morning also. I recommend all the participants to please get acquainted yourself with at least one plotting software. As an engineer, you must be acquainted with one plotting software so that you can visualize your results. So this is the temperature distribution captured before the steady state has been reached, and it is a line and flooded contour. Here I am now going to share with you animated results. So now I have plotted for only one instant here, but if we superimpose such instances, consecutive instances over each other and bring it in front of your eyes one by one, it can be helpful to create the movie. Now I am sharing with you here a simple movie. Are you able to see the movie now? You can see my temperature contours are changing. So it is passing through a transient process, transient heat transfer. But now you can see once the steady state has reached, the shape and bands of the color remain constant with respect to time. It's still transient, it's still going through unsteadiness. But now, see, now it has almost become a steady state. So these contours are now the steady state flooded contours. But now it has become steady. I will will again play it for you. Sorry, it has yet not reached the file. So what has been done? We have captured 100 frames like the one which I have shown you in the earlier slide. And those 100 frames are loaded in a single frame of a text plot of the plotting software. And then we can create the movie like this. Here, this x-axis represents the x spatial location, y-axis represents the y spatial location, and the time is going ahead as our movie moves ahead. So this is how I can obtain the solution. I can understand the variation in the temperature. This has been done for the situation wherein my boundary conditions are. Here the temperature is 100, here 200, here 300, and here is the 400. I have not shown here the legend, but legend can also be shown. But this one which I have shown was for one time instant only, and movie has been shared with you, which represent variation with respect to time for several time instances. Once the steady state is reached, the solution looks like this. Again, whether my finite volume methodology, which we have understood so far, we have tried to understand so far, works well after looking at these contours. Now see, the best way for and the solution, in fact, the analytical solution is also available for such kind of a problem. And the analytical solution suggests that the temperature at the center of the plate, square plate, should be average of the four temperatures. And the average of the four temperature, that is 100, 200, 300, and 400. The summation is 1000. 1000 by 4 turns out to be 250, and the temperature at the center of the plate is 250. So that means the methodology which we have adopted here is giving us the correct result. The other thing, I mean, do remember our objective is to understand the finite volume methodology. Of course, there is some kind of a heat transfer physics involved here, but then solution methodology is very important to us. What we have done, we have tried to understand the solution methodology for the problem. Finite volume solution. We have tried to understand the finite volume discretization of the problem. Whether it is working correct or not can be understood by the other things also. Like say, for example, this is a 200 degrees Celsius line, which is hitting the bottom. Bottom is at 200 degrees Celsius, but a line with maybe a temperature very close to 200, but not 200, will never touch this line. It will pass away from this straight line. So this is how we can obtain the temperature distribution, and we can indicate the temperature. This is one way of indicating the temperature distribution, because we cannot understand anything from the numbers as such. This solution has been especially obtained for 100 and 100 by 100 number of grid points along x and y direction. If you look at 100 by 100, 10,000 points, if you simply look at data, you feel that it is almost a junk. But then if you plot it, you can understand the variation of the temperature. So the purpose here is to understand the variation of the temperature. So that is something about the unsteady. Here I am again sharing with you the temperature distribution, which has been captured with a different boundary condition. So the purpose is that I want to communicate to you that the solution is always bounded by the boundary condition. The moment your boundary conditions are different, your solution is different. Here the solution is captured for solution at a particular time instant is captured, and the solution is with the boundary condition TB1 is 100 degrees Celsius. That is, this boundary is at 100 degrees Celsius. At top boundary, H is given to you and T infinity is given to you, 130 degrees Celsius. The thermal conductivity is given to you, that is 63.9. And here we have QW, that is a constant heat flux is supplied. which is 10 kilowatt per meter square, and the bottom is insulated. This is the situation, the temperature distribution at a particular time instant before before we reach to steady state solution is captured at a particular time instant, and that has been plotted, and the plot is in terms of line and flooded contours again. So you can see the temperature distribution can be, I mean, from this this is in the developing stage. Because this process, heat transfer process, is intrinsically steady state process, it may lead to a steady state solution. And we have already seen how the steady state solution looks like. So I have come to almost an end of the unsteady state heat conduction problem. In the morning, we have looked at the steady state conduction problem. And here we have looked at the 2D and unsteady state heat conduction problem. We have gone through the methodology for discretization of each and every term. We have looked at the algorithm. We have also looked at the equation in the physical way. We have also tried to derive it by using Gauss divergence theorem. And we have also talked about the solution methodology in terms of explicit and implicit methods. And we have talked about the stability criteria. The proof for the stability criteria is available in almost all the textbooks on computational fluid dynamics. So if you have now any questions, you may please go ahead. I will answer to few of your questions if you have. Okay, there are several questions in the chat box. Let me look at those questions one by one, and let me try to answer those questions. It's a question by Tumbanath. The question is, why stability condition is not required for explicit method, whereas required for implicit method? It's other way around. Stability condition is required for explicit method. It is not required for implicit method. So why it is required? Stability criteria is required for explicit method, because when we use explicit method like this with a large time step, it is the experience of the experience with the finite volume methodology which suggests that the solution diverges. If the solution diverges, we will not be able to obtain the temperatures, and hence certain criteria is required. I have not taken you through the proof for this stability criteria, but then the proof, I mean, it will require a separate session to take you through the entire proof. As I said, the proofs are available. The proof for stability criteria is available in the routine textbooks, which if you are interested, you can refer to. Even the book by Muralidhar and Biswas, wherein Professor Sharma has written one chapter, there the stability criteria, the chapter of stability criteria is available. Because the solution diverges, we need to use the stability criteria. That's what I can say at this point of time. Then the other question which is asked here is, does the solution converges for all the time steps? Yes, if we follow the stability criteria, the solution must converge for all the time steps. If we don't follow the stability criteria, maybe our solution will diverge. Then there is another question, what is the grid size you use in the problem? I said we have used 100 by 100 grid size for obtaining solution to these problems. Then time step and the time took for the execution. The time step we have considered is 0.001. In that time step, we have executed the problem and have tried to obtain the solution. But time, we have not noted down how much time, computational time it took for the execution. But it doesn't take too much of time to obtain. Maybe 2 to 3 minutes are taken to obtain the solution to such kind of problem. This being a simple problem, the time taken is fairly low. I think I have answered almost. Yeah, there is one more question in by Mr. Hemant Fegde. For implicit method, does the previous time instant act as a reference point? Yes, it acts as a reference point. I mean, it's an initial condition. So previous time instant is very important in case of an implicit method. Yeah, it is a reference point. I mean, previous time in unsteady state problem, let it be explicit or implicit solution methodology. In both the methodologies, the previous time instant act as a reference point. In case of a steady state problem, it is a initial guess, we say. Guess has to be decided by us. However, the initial condition is the real condition which we need to give. In FEM, there is a criteria for time step. Similarly, in FEM. Yes, maybe in FEM. I have not gone through FEM as such, but the criteria must be there. I mean, FEM needs a criteria if it is the solution is to be obtained explicitly. Is there any more question participant want to ask? Naresh Kumar. If you have any question, please go ahead. You may ask question by putting on your mic also. If there are no questions, maybe I will stop here for the session. But let me give you some instructions for our future this thing. We have to conduct the examination. We have for the program. What we are going to do, we will be conducting the examination with multiple choice questions. We will be forwarding you the the Google Sheet wherein the multiple choice questions will be placed. Maybe around 25 questions will be there, and you will have to solve those questions, and then the Google form will be referred for your examination as your solution to your examination. You will have to fill up the Google form. You will have to fill up the Google form before the closure of our FDP, that is on 2nd of October. So 2nd of October, 4 o'clock shall be the deadline. You will have to fill up the Google form. We will assess your answers, and based on that, you will be assessed. As per the guidelines provided by Atal, you need to pass the examination in order to obtain the certification. And the examination is to be passed with 50% marks at least. So you need to be present, and then your attendance is also essential for the certification. So these are some of the things. And the other important thing which I want to communicate is that you have to fill up the feedback form also. Yesterday, Professor Shirsagar, who is a co-coordinator of our program, has sent he sent you the feedback form again in the form of a Google form. He has sent it for the session conducted by Professor Atul Sharma. Today he will be sending the Google form for Professor Nandgaonkar also. You will have to give your feedback about both the speakers. Once I finish my sessions, all the sessions, he will be sending you the Google form for my rating also. That so that also you have to. So your this thing, the feedback is expected for all the speakers. So thank you very much for this session, attending this session sincerely, and thank you very much for your patience listening. I think I have come to an end. It seems that there are no questions as such. So I will stop, and we will come back at 2:30 At 2:30, we will be having the session by Professor Mr. Nelson. Session is at 2:30. The session will be by Professor Nagesh Chougule, who will be talking about the use of ANSYS software for dealing with the steady state and unsteady state heat conduction problems. As such, hands-on session is not possible because the participants may not have the software with them, but then if they get chance to deal with handle the software, how the software is to be handled for obtaining solution to such kind of problem, that will be dealt with by Professor Nagesh Chougule. So let us meet at 2:30. I shall stop here now because there seems to be no questions. So I will leave from the meeting for now, and we will be meeting again at 2:30. Thank you very much. Thank you for patience listening.